In this video, we're going to talk about the fundamental counting principle. The fundamental counting principle is a method for finding the total number of unique arrangements in which different events can occur. Let's take a look at a few examples. Here's our first example. How many possible combinations are there for a 4-digit PIN code if the first digit cannot be 0? To set it up, we know that we have a PIN number with 4 digits. The first digit can't be a 0. Now my possible choices are the digits 0 through 9. Since we can't use a 0 for the first one, the first digit in our PIN code, we'll take a look at what's left. What's left are 9 possible outcomes. So that goes here in the first spot. Next, we want to know how many possibilities are there for the second spot. And there would be 10. For the third spot, there's also 10. And for the fourth spot, 10. Because for each digit in placeholders 2, 3, and 4, there are no restrictions on the digits. Once we get to this point, we simply multiply our values together. 9 times 10 times 10 times 10. In other words, 9 times 10 to the third, which is equivalent to 9 times 1,000, or 9,000. So there are 9,000 different possibilities for this 4-digit PIN code. In this example, we want to know how many different ways can the letters in the word statistics be arranged. Looking at the word statistics, I see that we have 10 letters in the word. However, out of those letters, ten letters in the word, and 3 letters have repeats. So, we'll set it up by taking 10 factorial, which represents the total number of letters in the word, divided out by 3 factorial times 2 factorial times 2 factorial. These values represent the number of times a letter repeated in the word. For example, S repeated 3 times, so we have 3 factorial. T repeats 3 times, not 2, so we have 3 factorial again. And then the letter I repeats twice. Next, we simply work it out. There is a factorial key in your graphing calculator if that's what you're using, but we're also able to work these out by hand without too much trouble. So 10 factorial is the same as saying 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. All divided by 3 factorial, which is 3 times 2 times 1, another 3 factorial, for 2 factorial, we write 2 times 1. Next, We cancel out common factors in the numerator and denominator. And this leaves us with 10 times 9 times 8 times 7 times 6 times 5 times 4 in the numerator. And in the denominator, we have, simplifying this expression, we get 604,800 divided by 12. These numbers came from multiplying across the top of this numerator and the bottom of this denominator. Dividing this out further, we get 50,400 different ways. Let's take a look at one more example. Suppose I own a restaurant, or tonight I'll be serving 2 entrees. We have the steak and we have the pasta. Along with the entrees, there's a choice of one of 2 sides, either soup or salad. We also have a choice of 2 desserts, ice cream or pudding. So when we set up a tree diagram like this, we see that we can so here we have 2 entrees, choice of soup or salad, choice of ice cream or pudding. The total number of items in the sample space can be found by either counting the endpoints of a tree diagram, which can be time-consuming, or using the graphing calculator, or just a regular scientific calculator. What we do is we take the number of choices for entree, 2, times the number of choices for just a regular work week, 2, and then we multiply that again by 2 for the choices for dessert. Eight powerful choices for our meal combinations. 2 times 2 times 2, which equals 8. This concludes our example. I hope you found it helpful, and we'll see you next time.